Mr. Tarrou. In this video, we're going to be doing 4 examples of factoring involving variable exponents. It's kind of a third video in a series, so I'll put the links in those other 2 videos below, and you'll also find a link to my YouTube channel and my website that has all of my lessons organized by subject, and within those subjects by chapter, so not just a big long playlist. Okay, so let's go ahead and get started. So we're going to be strengthening, reviewing our factoring skills, and dealing with some common patterns. We have here with number 1, which is going to be some kind of factor of a squared minus b squared is equal to a plus b times a minus b. We're going to have number 2 here, a 3-term expression, and we're going to hopefully understand how we can recognize that it is in sort of a quadratic pattern. And I say sort of because I'm going to set this up as if to recall your skills of factoring polynomials or trinomials, though these do not have positive integer exponents. They're not really technically polynomials or even trinomials, in case I slip and call it that. So let's see here. So we'll be basically reviewing our skills of factoring trinomials where our leading coefficient is equal to 1, and you'll see how that develops. Number 3, we're going to have to remember how to factor patterns of ax squared plus bx plus c. Again, factoring in that quadratic pattern, we have to do a little work to make that show up, but our leading coefficient is greater than 1 or not equal to 1. Not equal to 1. And here with number 4, we're going to review some completing the square process to, again, factor this 3-term expression that is in sort of that quadratic pattern. Okay, so let's go ahead and get started. Now, as we look at number 1, we have got 25 minus 9 to the x power. Now, you might recognize the 25 as being a perfect square, and you might be tempted to look at that 9 as a perfect square, and actually that's kind of important, but when you have exponents, you want to see that, and remember, let's see here, that when you take the square root of some base to a power, now here our base is a variable, how you're probably used to seeing these problems, and we have a constant power of a. Well, if we write this square root of x to the a power, that's going to be x to the a over 2. Remember, when you write rational or fractional exponents, we have the power that's being applied to that base in the numerator, and we have the index or the root, which is becoming the denominator. Okay, so why do I bring that up? Not that you have to have an even power here on the 9 to be able to recognize this as a difference of squares, but as you start being introduced to problems that are not just like an x squared minus 16, let's say, as an example, they do generally give you even powers there to move into some more complex situations. So what I want to do here is I want to write 25 as that something squared, just to really make that pattern stand out for you. And now with the 9, we can write that as something squared. Of course, that's going to be 3 squared, which is then raised to a power of x. And we're going to also have to know some properties of exponents here. These are really fun problems because they make you have to think about many areas of mathematics that you've learned recently and bring them together into one problem. So we have 3 raised to a power of 2, which is then raised to a power of x. Well, that's the power rule for exponents. We can rewrite this as 5 raised to the 2nd power minus 3 times 2 to the x. And though this is an expression, we can see that, again, not that it really has to be, but that this power is even because it's any number multiplied by 2, which by default, in a sort of mathematical expression type way, this is sort of a general form representing an even number. I should write this as 5 squared minus, and then 3 to the x power squared. There you go. That's a little better. So here we can see that the a is going to be 5, and b, I had that technically actually written incorrectly, is going to be 3 to the x power. when I do these for myself, and I'm not trying to explain every single minute detail that's going on, I don't normally write that A equals B equals stuff on the side, so I flub that up a little bit here. So now we're looking at A, which is 5, minus B, which is going to be minus 3 to the x power, and then times A plus B, or 5 plus 3 to the x. And that is, number 1, just in factored form. Now, if this thing was set equal to 0 and we were solving this equation, we'd be setting each of these factors equal to 0 and then finishing that up, which we are going to take a look at with number 4. Your extra difficulties coming from these problems is coming from the fact that you're used to having variable bases and not numbers, not being able to actually see what that common base is with those powers applied to it. Usually the power is the one that's constant. So number 2, we have our 9 raised to the power of x minus 8 times 3 to the x plus 15. Now, I said at the beginning of the video this was going to be a quadratic pattern. Close to, it's not a polynomial, but close to that. We can recall on our skills that we learned of factoring quadratic polynomials. Well, we see a base of 3 and we see a base of 9. And like when you think about those quadratic polynomials, we had that common base. It was like an x squared and then an x to the first, where we had a common base raised to some different exponents. So what we're going to do is we're going to write the base 9 as a base of 3, like we just saw me do in the previous problem. So we have 3 squared, which is equivalent to 9. I'm just going to copy the rest. 3 squared to the x power minus 8 times 3 to the x plus 15. We're going to go ahead and bring this x down using those powers of exponents, or the property, power property for exponents, which is going to be 3 to the 2x power minus 8 times 3 to the x plus 15. And we could write this as 3 to the x power, then all in that quantity squared, but I'm going to leave it in this format. This is going to factor the same way that this would factor. It's some common base to a power. Now, this isn't the same question, but like to tie in with skills you already know, minus 8 times that same base, base 3 here, well, and maybe say at the end of Algebra 1, you'd see that common base written as an x. And this exponent is half of this exponent. Well, if I write x squared minus 8x to the first, and we don't normally write that exponent of 1, this exponent is half of that exponent. So it is the same pattern, and then plus 15. Well, when you see a quadratic polynomial, a trinomial, that has a leading coefficient of 1, all you have to ask yourself is what factors of positive 15 add to negative 8? That's going to be negative 3 times negative 5, and you can check it. But how is this the same as this expression, this trinomial, written with an exponent of 1? Well, the key to factoring where the variable is in the exponent is to really highlight what are the coefficients along this three-term expression. I really want to call it a trinomial, but we don't have a guarantee of those positive integer exponents. You really want to clearly identify for yourself what are the bases and what are the coefficients of what we know as previously in the sort of more basic value level of factoring, the a, the b, and the c. Well, a is going to be 1. The coefficient of the base 3 is 1. The coefficient of this base 3 is negative 8, and then we have a coefficient of 15. So again, just trying to link this with previous knowledge and to let you see that this section here is a review of your factoring skills. Our a would be 1, our b would be negative 8, and our c would be 15. And I'm going to continue to do this through the rest of the examples where I'll highlight the coefficients and separate those from the bases, which we don't normally see as a constant. So again, what factors of 15 add to negative 8? Well, we're going to set up our two binomials, or binomials, quotation mark. The square root of 3 to the 2x, the square root of 3 raised to the 2x is going to be 3 to the x power. just like we have the square root of x squared is equal to x, written twice. Factors of 1, coefficient of 1, factors of 1 are just 1 and 1, so whatever. And we have the 15 coming up as, again, negative 3 and negative 5. And you can double check it. 3 times 3 to the x times 3 to the x is 3 to the 2x. 3 to the x times negative 5 is negative 5 times 3 to the x. And then we have a negative 3 times 3 to the x. And without seeing where you want to combine those factors with a common base of 3, we can see that negative 5 plus negative 3 is going to give us a negative 8 times 3 to the x power. And then negative 3 times negative 5 is positive 15. Okay, so there is our second example factored. See, it's just a review of skills you already know. Now, for number 3, we have one step up in difficulty here, each of these getting a little bit harder as we go. We have 4 times 25 raised to the x power minus 35 times 5 to the x power equals 9. Okay, well, our coefficients here are 4, negative 35, and 9, but we're not ready to factor this expression, which now is actually going to be an equation. So we'll go ahead and finish this up and solve it. Let's set this thing equal to 0 and solve this equation. So we're going to have 4 times 25 raised to the power of x minus 35 times 5 to the x. We're going to bring this 9 over with subtraction and have minus 9 is then equal to 0. So how do we solve this? Well, we have a base of 25 to an x and a base of 5 to an x. Maybe this is not solvable, but this is pretty easily rewritten to create that quadratic pattern, because 25, of course, is created by or equivalent to 5 squared. So we can write both of these factors that have a variable exponent. We can write them both to have that same base and allow us to find an exact value, an exact solution to this what's going to be a quadratic without the aid of a calculator. So we have 4 times 5 squared, then raised to the x power, which I'm going to go ahead and write that as 5 to the 2x power, minus 35 times 5 to the x minus 9 is equal to 0. Now, you're watching an advanced factoring video, but in case you need this, and I actually need to do this anyway for myself, whenever I have a quadratic pattern, we have 3 terms, and we have that, again, that common base of 5, and this power is twice as big as this power, and then there's no base of 5 left in the last term. I like to go through this process of, we take the leading coefficient and the constant and multiply those together. So we have 4 times, we'll do this in blue because it's a little bit of scratch work, 4 times negative 9 is negative 36, and now I'm going to be looking for factors of negative 36 that add to negative 35. So they need to multiply, I need 2 numbers that multiply to negative 36, but then also add to be negative 35. And there's many options here, like we could do 3 times 12, or again the 4 times 9, but when you add 4 and negative 9, you get, well, negative 5, but we can work with this. We've got 1 times negative 36, which equals negative 36, but we also have 1 plus a negative 36 is equal to negative 35. So here, the 1 and the negative 36, I want to rewrite this middle term instead of being 1 term as 2 terms, and then we're going to continue factoring by grouping. So we have 4 times 5 to the 2x plus 1 times 5 to the x power minus 36 times 5 to the x minus 9 is equal to 0. Now, within the first 2 terms, What common factor can you take out? Well, there's no common factor between 4 and 1, but we do have a base 5 to a power of 2x, and we have a base 5 to a power of x. So we're going to factor out that lowest power. We're going to factor out that 5 to the x. So now we're going to start recalling some of those skills that we just reviewed where we factored sort of quote-unquote monomials dealing with variable exponents. So we're going to take out that lowest power, that 5 to the x, and it has a coefficient of 1. So 4 divided by 1 is going to be equal to 4. And 5 to the 2x divided by 5 to the x, well, when you divide like bases, you subtract those exponents. So 2x minus x is going to be 1x. So 4 times 5 to the x. Let's go ahead and highlight that coefficient in red. And then plus 1, because 5 to the x power divided by 5 to the x power is just going to be equal to 1, which I guess I could keep as white, since it's not really a coefficient of a variable fixed space. Now, what common factor can we take out of the last two terms? Well, we have a negative 36 and a negative 9. We really want those coefficients of positive 4 and positive 1 to show up again. So let's factor out a negative 9. And get, I want to make everything red. Negative 36 divided by negative 9 is positive 4 times 5 to the x power. Negative 9 divided by negative 9 is going to be a positive 1. And now we went from 3 terms down to up to basically 4 terms. And now that we factored out by grouping, we now have 2 terms. We've got this big mess here minus this second term. Each of these 2 terms have a common factor of 4 times 5 to the x power plus 1. So like we pulled out the 5 to the x power, like we pulled out the negative 9, we're going to pull out a common factor or divide out a common factor of 4 times 5 to the x power plus 1, and leaving us with taking this factor out of the first term. That's going to leave us with a 1 times 5 to the x. And going to the second term, factoring out the 4 times 5 to the x plus 1, that's going to leave us with a minus 9. Okay, so since number 3 was the first example that gave us an equal sign, let's go ahead and finish solving this quadratic pattern equation. We're going to set our first factor equal to 0. We're going to subtract by 1. And at this point, whether it's now or after you divide by 4, and I hope you don't have to go as far as grabbing your calculator to try and finish this, we have a positive base raised to a power, which means exponents, though you can sometimes, have fractional exponents, it does represent repeated multiplication of the positive base of 5. So positive 5 multiplied by itself any number of times, even if it happens to be a negative exponent or a fraction, repeatedly multiplying by a positive 5 in some format, times a positive number is never going to give you a negative answer. So the solution to this factor is there isn't one. It does not exist. But for a second factor here, we have 5 to the x power minus 9 equals 0. And now we're going to add both sides by 9. And remember that we learned about natural log and logarithms, common logs, so that we could solve equations where the variable is in the exponent. So we're going to take the natural log of both sides now. Or you could do common log as well. Natural log just happens to be one less letter for me to write. Okay, and now we're going to use that power property of logarithms that's going to allow us to take this x and move it out front. Remember, you get exponents from logarithms, and so the natural log of 5 is going to give you an exponent, which is then raised to another exponent. And as we demonstrated here earlier, actually in the previous example, we can just bring that stacked exponent down. And now we're going to undo that multiplication of the natural log of 5 to the x. We're going to undo that, of course, with the inverse math operation of division. And get x is equal to the natural log of 9 divided by the natural log of 5, which is the exact form of this answer. So I'm writing an equal sign. If I were to put natural log of 9 divided by the natural log of 5 in my calculator and get a decimal, That's an irrational number. No matter how many places after the decimal you go out to the right, you're going to get an approximation, so I'd have to do like a little squiggly equal sign instead of an x equals. All right, last example. Thank you for sticking this far through the video. If you have, now let's step it up a little bit more. The difficulty, that is. Alrighty then. So for our last example, we have 9 to the x power plus 3 to the x plus 1/2 power is equal to 9. Now this really kind of doesn't seem to be the same pattern as the previous ones. I do have 3 terms, but it doesn't look like this exponent of x is twice the size or value of x plus 1/2. But we do have a base of 9 as opposed to a base of 3, so let's get that out of the way. And we'll move the 9 over with subtraction. So we have 3 to the 2x power plus 3 to the x plus 1/2 power minus 9 is equal to 0. Okay. Well, we have 3 terms now, and our coefficient here is 1 and a coefficient here of 1, and we have that minus 9. But it doesn't fit that quadratic pattern yet because 2x is not twice as large of a power as x plus 1/2. But we still have another tool in our box. Remember, this is a review of lots of things: factoring, logarithms, powers of properties of exponents. When do you add exponents? Which is what we have here with under this or on this base of 3. You add exponents when you multiply with a common or like base. So our middle term here can be rewritten as 3 to the 2x power plus 3 to the 1/2 power times 3 to the x minus 9 is equal to 0. So what we're really looking at here is a 1 times 3 to the 2x plus the square root of 3 times 3 to the x power, and then minus 9 is equal to 0. So now we have a quadratic pattern, a 3-term quadratic pattern where we have a common base of 3, we have an exponent again that's twice as large as this exponent, and we have a constant. So we can say that a is 1, b is the square root of 3, and c is negative 9, and we have 2 ways of doing this. You can just pull out that sort of tried and true quadratic formula and say that we have, with our common base of 3 to the x, and maybe here if we're going to review quadratic equation and completing the square, might be a good idea to see this as 3 to the x squared. So if you were to write the quadratic formula, it would be, instead of x equals, it'll be 3 to the x is equal to the opposite of b plus or minus the square root of b squared minus 4ac over 2a. Now we can finish that, and then when you get the 2 numerical values that you get out of this expression, you're going to write with the plus or minus. You'll write those as separate little equations with a 3 to the x equals each of those numbers and solve and finish with the probably natural log or common log function, whatever you prefer. I'm going to stick with the book that's inspiring these problems that I'll be teaching out of next year and work through this. And plus we might need the review. Work through this by completing the square as opposed to just jumping straight to that formula. By the way, if you don't know it, the quadratic formula is just simply derived by the completing the square process. So the completing the square process, what are we going to do? We're going to move the 9 back over to the other side. Keep highlighting those coefficients in red. Leave some room for the completing the square value that we're going to come up with here in a minute. Remember, with completing the square, you take half of b and you square it, and you add that that value to both sides of this equation. So we have half of the square root of 3 squared is going to give us a value of 3/4. So we're going to add 3/4 to both sides of this equation. And when you complete the square, what you set up on the left-hand side, if you remember from algebra, is a perfect square trinomial. You set up a trinomial, though again, this is not technically a trinomial, that is factored by simply taking the square root of the first term the square root of the last term, and keep the middle sign. So our factored form of the left-hand side is going to be the square root of 3 to the 2x power is 3 to the x power. We already have the square root. We know what this the 3/4 came from. It came from the square root of 3 over 2. And we're going to keep the middle sign. So we have plus square root of 3 over 2 squared is equal to, now we're going to find a common denominator. And we have 36 times 36 plus 3 is 39 over 4. We're going to get rid of this power of 2 by square rooting both sides. And we are going to get a little tight on space. We're going to have 3 to the x power plus the square root of 3 over 2 is equal to the positive root here, which is going to be the square root of 39 over 2. Now we're going to continue to solve this, but we have a second equation to remember, which is going to be, or solution to look for and consider. We have 3 to the x plus the square root of 3 over 2 is equal to the negative answer, which is going to be negative square root of 39 over 2. And let's go ahead and get this one out of the way because we're going to have an issue. We're going to subtract both sides by the square root of 3 over 2. And as we see here, we have a positive base of 3 to a power of x, representing a repeated multiplication of some number of times of a positive base, and that is never going to equal a negative answer because we have negative 39, square root of 39 over 2 minus the square root of 3 over 2. So this has no solution. So we're going to get this out of the way to make sure we don't run out of room and focus on the one real solution that we can get from this problem. Because we are looking for real solutions. We're not considering imaginary here. That's why I'm saying that solution does not exist. There is arguably an imaginary solution, but yeah. So we're going to subtract both sides by the square root of 3 over 2. And we are going to get an approximated answer here because, not that we can't write it in an exact format, but the square root of 39 over 2 minus the square root of 3 over 2 is going to give us approximately 2.2565, right off the top of my head, not really my notes. And now this is an approximated value, so I'm going to switch to that approximate symbol. We're going to take the natural log of both sides and drop the x down. Divide both sides by the natural log of 3. And x is approximately equal to 0.74077. And here with our problem again, 3 to the 2x power is going to have a domain of all real numbers. We have 3 to the x power, so we have a domain of all real numbers. Not that it's ever a bad idea to check your work by plugging it back into your original equation to make sure the two sides are equal to each other, but we don't have an issue with this possibly not falling within the domain of our problem and thus being an extraneous solution. So, thank you for getting to the end. I'm Mr. True. Bam! Go do your homework.